Hello class. So we're going to go ahead and do 12.4, the cross product. This is another operation that you can do with vectors. With the dot product was multiplying vectors and then seeing that they became a scalar. The cross product, what it does is it's mapping two vectors. So the operation that we're going to do is, if you do the cross product, which this is the symbol, it looks like a multiplication symbol, but it actually means cross product when you're dealing with vectors. So A cross B ends up being this. It ends up being the second term from the first vector times the third term from the second vector minus the third term from the first vector minus times the second term from the second vector, and then following that, that's going to give you the first term. Then for the second term, it's the third term from the first vector times the first from the second minus the first term from the first vector times the third, and then here's the operation for the last term. I'll do an example just so you guys can see, and I'm going to show you two ways to do it. Okay? The first way that I'm going to do it, I'm going to use this formula, and then the second way I'm going to do it like you guys did in Algebra 2 with a determinant. So let's go ahead and see this. So A cross B is going to be, so remember, it's the second term from the first times the third term from the second. So I'm going to get 3 times a negative 5 minus, and then it's the third term, so it's 4 times 7, because I'm getting the 4 from here and the 7 from here. That is going to be the new vector, the first term from the new vector. Then we're going to get 4 times 2 minus 1 times a negative 5. And just so you see that, it's 4 times 2 minus 1 times that negative 5. And then the last one is going to be 1 times 7 minus 3 times 2. And that's our vector. So when we clean that up, we're going to end up with a negative 15 minus 28, 8 minus 5, 7 minus 6, and so our resulting vector is going to be negative 43. Negative and negative, this should be a plus. 13, and then 1. So that's one way to do it. The other way to do it is to use the determinant. And so with the determinant, I'll write this down just so you guys can have it. And again, this is from Algebra 2. I'm going to go I, J, K, those being the unit vectors for the X, Y, and Z axis. And then the first vector, which is going to be 1, 3, 4, and then 2, 7, negative 5. And now I'm going to find the determinant. So I don't know if you remember this, but I'm going to have the first minor matrix is going to be created by these 4 numbers. So I'm going to have I, which eliminates this row and this column. This column and this row. And so what's going to end up happening is I'm going to get 3, 4, 7, negative 5, and then I. And then it alternates signs, so it's positive, negative, positive. Now I'm going to use J, So this is getting eliminated with this. And so the minor matrix is going to be 1, 2, 4, negative 5. Or you can think of it as 1, 4, 2, negative 5. And so I'm going to get 1, 4, 2, negative 5 as my minor, with J as the representation. And then, like I said, alternating signs, it becomes a plus. And my minor matrix is going to be 1, 3, 2, 7, and then K. So what I'm going to end up with is, if you remember the minors, the determinant is this times this minus this times this. So I'm going to get negative 15 minus 28i, and then 1 times a negative 5 minus 8, that's my J, and then plus, I'm going to get 7 minus 6, that's my K, and so we see we're going to get negative 43i plus 13j plus 1k. And that is the same matrix as the one before. Now remember, that represents I, that's j, and that's k. So this and this are in fact the same. And the cross product is a vector, while remembering that the dot product is a scalar. So please don't forget that. That's important. Okay, there's a theorem, and the theorem says that A cross B is orthogonal to both A and B. So just so you guys can quickly understand this, I'm going to draw a picture of, So this is our new three-dimensional world we're living in, right? And so what ends up happening here is this is X, Y, and Z. So if I take the cross product of any of the axes, or if I take the cross product of the unit vectors I, J, and K, what ends up happening is something pretty cool. I know that this is perpendicular to this. I know this is perpendicular to this. And I know that this is perpendicular to that. So what ends up happening is when you have cross products of two vectors, the resulting vector is going to be orthogonal, or you may not know what orthogonal is, perpendicular to the two vectors. I'll be using orthogonal, so just remember that the cross product is going to give me a vector that is orthogonal to the two vectors that are created. Okay, there's a theorem that says that the angle, that if theta is the angle between A and B, between 0 and pi, then the magnitude of the cross product is equal to the magnitude of each of the vectors times sine theta. Just a picture so you can see. So you guys can see this. It's going to look like this. If this is B and this is vector A, this is the angle that's being created. And then from the end to the vector A, that's magnitude of B sine theta. But this is just going to be useful for us to be able to find angles between the two vectors and the cross product. Two non-zero vectors A and B are parallel, and they're parallel only if their cross product is 0. So this is kind of an important big idea. If the cross product between two functions or two vectors is 0, then the result is that we have two vectors that are parallel to each other. So I'll see, it'll be in the homework for you, but if I had given you a vector A here and a vector B here, and these are in fact parallel, then their cross product has to be equal to 0. And that's going to be the case, okay? Some other useful information that we're going to be using with this information is that the length of the cross product of A cross B is equal to the area of the parallelogram determined by the two vectors. So the cross product, right, the length of it, so we're saying the magnitude of it, is going to be, that scalar number is going to be the same as the area of the parallelogram that's resulted. So if I have, here's vector B, here's vector A, if I make a parallelogram, the area of that parallelogram is the same as the magnitude of the cross product of A and B. I'll do an example in just a second. And there's going to be some derivations to this too. If we have a parallelogram, if you cut the parallelogram in half, instead of having a parallelogram, what we're going to end up having is a triangle. And so then that would mean that half of the length of the cross product would be the same as the area of a parallelogram. And I'll do an example of that in just a second. Okay. So now, in this example that I'm trying to show, I want to find a vector, or the vector, that is perpendicular to these 3 points. Okay? And one thing that's important to remember about these 3 points, they form a plane, and the reason they form a plane is because they're not linear. So if you have 3 nonlinear points, that forms a plane. And so now we want to be creative about how we use our points to create our vectors. So I'm going to use P and Q. And I'm going to, so P and Q, to find that vector, we should remember that it's going to be -2 minus 1. I'm going to do it, I'll do it as a clean vector instead of as I, J, and K. And then I'm going to go 5 minus 4, and then I'm going to go -1 minus 6. Now, for those of you who don't remember, if I'm going P and Q, the vector that's resulted from the 2 points is going to be the difference in the x terms, comma, the difference in the y terms, comma, the difference in the z terms. So that's going to give me my vector P2Q, which will end up being -3, comma, 1, comma, -7. And then I'm going to go from P to R because I want the initial point to start at the same place. So I'm going to use P both times. So I'm going to go, okay, the vector is going to go 1 minus 1, -1 minus 4, and then 1 minus 6. And so that's going to give me a vector that's going to be 0, -5, -5. Okay? So now I have 2 vectors, and since we want to find a vector that's perpendicular to it, we now know that the cross product of the 2 vectors gives us a vector that is perpendicular to both. So since it's perpendicular to both, it's going to be perpendicular to the plane that's created by these 3 points. I'll just kind of draw a picture so you guys can see. So if I had, here's a point, here's a point, here's a point, and I had these 2 vectors, this ends up forming a plane, right? The resulting vector of this guy is going to be something that's going to go, how do I draw this so you guys can clearly see it? It's basically going to be shooting straight up and down. So it's coming like through the page, perpendicular to that plane. Okay? Now, how to do that? We're going to take PQ, the vector PQ, and cross it with the vector PR. And the way that I'm going to do it is, instead of using the formula, I'm just more comfortable using the determinant. So I'm going to use the determinant. So I'm going to go I, J, and K. And then I'm going to go vectors -3, 1, -7, and then 0, -5, -5. And then do the minor determinants. So I'm going to go 1, -7, -5, -5. And that's going to be my I. Minus -3, -7, 0, -5. That's going to be my J. And then plus -3, 1, 0, -5. That's going to be my K. Well, that's going to give me -5 minus 35. That's my I. That's going to be 15 minus 0. That's going to be my J. And then this one's going to be 15 minus 0. That's my K. And so I'm going to get -40I minus 15J plus 15K. This is the vector that's perpendicular to this plane. Okay? I know it's kind of a lot. First we had to find two vectors, and we went from one point as the initial, going to the other 2 points, finding their difference so that we could get the two vectors. Then we had to take the cross product. From the cross product, that gave us the vector that's perpendicular to both those vectors, but also perpendicular to the plane that's created by the 3 points. Okay. Now the next thing is, I wanted to show you guys how to find the area of the triangle with these vertices. And so I don't want to reinvent the wheel. It's the same problem. So the thing that I can do, we need to remember that it said that the magnitude or the length of the cross product is the area of the parallelogram. Well, this isn't a parallelogram, it's a triangle, so we're not going to want the full parallelogram, we're going to want half of it. And so I know that the cross product is that value right above, the -40I minus 15J plus 15K. If I want to take the magnitude of it, we remember that it's that formula. So I'm going to go -40, that quantity squared, plus a -15, that quantity squared, plus 15 squared. That's going to give me 1600 plus 225 plus 225. And that's going to give me 2050, which is approximately 45.3 units, right? And this is just a scalar number, but this, remember, is the same as the area of the parallelogram. And since that's the same as the area of the parallelogram, the triangle that we're getting from this is going to be half of that. So I'm going to go, that area is going to be 45.3 divided by 2, which will approximately give me 22.65, whatever the units are, squared. Okay? Then from there, I just want to point out there's some properties that I want you guys to know, and it's important. Again, this one is a scalar. All the others, so A, B, and C, are vectors, but D is a scalar. So just think of it, this is a scalar, so that's a scalar, Oh, my bad. This right here is a mistake by me. It's a good thing I noticed. This should be D. Okay, so really what's happening here is it's just showing that the commutative property holds, the associative property holds for both multiplication and addition with the cross product. And then the cross product of the cross product is actually pretty interesting. So notice this one here, the cross product ends up being a dot product times a vector minus the dot product times another vector. So what these end up being is that ends up being a scalar, that ends up being a scalar, which is important. Let's see what else. Ooh, and in number 1, I want you to notice something. So the way the cross product works is if I have A cross B to go B cross A, I need to do a negation because of direction mattering, right? So that's really, really important that we know and understand that. So please make sure to pay attention to these rules, and it's great to have electricity back. I'm sorry for the delay. If you guys have any questions or you have any needs, please let me know. I'm willing to meet with the class if needed. Just let me know. Okay? All the best.